And now in this lecture we find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, we know that this is 9/7 AC, that is equals to 5 units in its length. This is 9/7 CB, that is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So we start with the first method, and we join points B and P together by a straight line. In the next step, I copy the white semicircle with the peripheral angle that was created by joining points B and P together by a straight line, and we will implement on the white semicircle rule 7. So actually, this is the white semicircle that I copied from the original drawing. By joining points P and B together by a straight line, we created the peripheral angle APB. This is peripheral angle APB. And you know that AB is the diameter of this semicircle. So I write it down. AB is the diameter of the semicircle, or the diameter of the white semicircle. AB is the diameter of this white semicircle. And we have here peripheral angle APB is subtended on AB, that is the diameter of this semicircle. Again, peripheral angle APB is subtended on AB, that is the diameter of this semicircle, and therefore we can implement here rule 7. Now pick quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle, and we have a peripheral angle ACB. This peripheral angle ACB is subtended on AB, that is the diameter of this circle, and therefore according to this rule, rule 7, peripheral angle ACB must be equal to 90 degrees in its size because of the fact that it is subtended on AB, that is the diameter of the circle. So whenever we have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB that is subtended on AB, that is the diameter of this semicircle. Therefore, according to rule 7, peripheral angle APB must be equal to 90 degrees in its side. So this peripheral angle APB must be equal to 90 degrees in its size. according to rule 7. Likewise, we join points P and C together by straight line. So in the next step, I'll copy the green semicircle in a new page and we'll implement rule 7 on the green semicircle. So actually, this is the green semicircle, the comment from the original drawing. AP is of course the diameter of this semicircle, the green semicircle. So write it down. AP is the diameter of this green semicircle. And we have here peripheral ACP. This is peripheral ACP that is subtended on AP, that is the diameter of this green semicircle. And therefore, according to rule 7, peripheral ACP must be equal to 90 degrees in its size. Okay. You can see from the drawing, this is angle A. This is angle A. That is a common angle. It belongs both to the green triangle APC and it also belongs to triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we define the size of this angle, the common angle, angle A, as alpha. So according to our definition, the common angle, angle A, equals to alpha. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we define the common angle, angle A here is alpha. So in the green triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. In the next step, I copy this green right triangle APC and also this right triangle APB in the new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are called from the original drawing. So in the next step, we'll prove that those two right triangles are similar to each other according to angle similarity rule. So we'll prove that this is the right triangle APB, and we'll prove that it is similar to this right triangle APC. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB, the right triangle APB. And it is equal to this angle, that is actually angle ACP, in the green triangle APC. So repeat again, I actually found out that angle APB in the right triangle equals to angle ACP in the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both angle alpha. That is to say, angle alpha is a common angle that belongs to both angles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. So if we relate to angle alpha as it belongs to this right triangle, it will be defined as angle PAB. And it belongs to itself. So if we relate to angle alpha as it belongs to this right triangle, it will be defined as angle PAC. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ABP in the right triangle APB, and it is equal to this angle, that is actually angle APC in the green triangle APC. Repeat again. Angle ABP in the right triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually prove that all the figures of this green right triangle APC are correspondingly equal to all the figures of this white triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually prove that the right triangle APB is similar, this is the sign of similar, to the right green triangle APC, according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derived that the following relationship exists between their sides. But before that, what is the length of side AB? From the drawing, it is very easy to see that AB in total equals to 5 plus 1, that is 6. AB equals to 5 plus 1, that is 6. And AC equals to 5 according to what is given as the question. So, from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. That side AB in this right triangle over side AP in the green triangle equals to side AP in this white triangle over side AC in this green triangle. Repeat again. If we found out that AB over AP equals to AP over AC. AB 6 over AP. AP is the missing side, so we leave it as it is. And it is equals to AP over AC. AC is 5, so AC by 5. In conclusion, we found out that 6 over AP equals to AP over 5. Here we cross multiply this equation, and we get that 5 times 6 is 30, so 30 equals to AP times AP, that is AP squared. So 30 equals to AP squared. We take out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. So here this is side AP is equals to the square root of 30 units in its length. We already found out that AP is the diameter of this green semicircle. If AP is the diameter, it means that AP over 2 is the radius. Okay, so the radius of this green semicircle is, so we define the radius as R, so the radius of this green semicircle R equals to AP, the diameter AP over 2. The diameter AP is square root of 30, and square root of 30 over 2 is the radius. So R, the radius of the green semicircle, equals to the square root of 30 over 2 units. And our mission is to find out the area of this green semicircle. So the area of the green semicircle is equals to pi r square over 2. Okay? It is equals to pi r square over 2. So it is pi and r is square root of 30 over 2, therefore r square is square root of 30 over 2 square divided by 2. We'll open the brackets of this expression and get that the area of the green semicircle in total equals to pi, and square root of 30 square is 30 divided by 2 square, that is 4 divided by 2. So the area of the green semicircle equals to pi, and 30 over 4 over 2 equals to 30 over 4 times 2. So the area of the green semicircle equals to, here we have 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75, so in total this expression equals to 3.75 pi. Or in terms of numbers, it is 11.78 square units. In conclusion, we actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line. In the next step, I'll copy the white semicircle in the new page, and again we will implement all 7 on the white semicircle. So actually, this is the white semicircle. This is the white semicircle that I call it from the original drawing. We already found out in the first method that AB is the diameter of this white semicircle, so I write it down. AB is the diameter of this white semicircle. By joining points P and B together by a straight line, we can deduce peripheral angle APB. This is peripheral angle APB, and it is subtended on AB, that is the diameter of this white semicircle. Therefore, according to rule 7, peripheral angle APB must be equal to 90 degrees in size. So this angle, peripheral angle APB equals to 90 degrees in its size. So we have here 97 BP is perpendicular to PA. Again, 97 BP is perpendicular to PA. Okay, so here this is 97 BP and it is perpendicular to PA. So this angle equals to 90 degrees. According to rule 7. So I copy the green semicircle with line segment BP, and we will analyze the green semicircle with the line segment BP. Okay, this is the green semicircle with line segment BP that are coming from the original drawing. This angle is angle APB that according to rule 7 is equal to 90 degrees in its size. Okay. AP, we already found out that AP is the diameter of this green semicircle. If AP is the diameter, it means that AP over 2 is the radius. Again, AP over 2 must be the radius of this green semicircle. We define the center of this green semicircle. This point is point O. So point O is the center of this green semicircle. Point P is the point of the green semicircle itself. Therefore, OP is the radius of this green semicircle. We define the radius OP as R. Therefore, OP equals to R according to our definition. So in the drawing, we have line segment BP is perpendicular to the radius PO of this green semicircle. Again, line segment BP is perpendicular to the radius PO of this green semicircle. And therefore, we can implement here rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, we have the radius OM is equals to R. And we have here this line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO. And whenever you have a line segment that is perpendicular to the radius, this line segment AB is defined as a tangent. Again, line segment AB is defined as a tangent because it is perpendicular to the radius MO. Okay, repeat again. Whenever you have a line segment that is perpendicular to the radius, it is defined as a tangent. This we have here tangent AB, this is tangent to this circle at point M. So we can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP. This is line segment BP that is perpendicular to the radius PO. Again, line segment BP is perpendicular to the radius PO of this green semicircle. And whenever we have a line segment that is perpendicular to the radius, this line segment PB must be defined as a tangent. Therefore, PB is the tangent of this green semicircle, and the point of tendency is point P. Again, repeat again, according to rule 1, line segment BP must be tangent to this green semicircle because it is perpendicular to the radius PO. Okay, so line segment BP is tangent to this green semicircle at point P, according to rule 1. In addition, in the drawing we have from the common external point B, we have the straight line that cuts this semicircle at 2 points C and A. In this way, we created chord AC. So from the common external point B, we have chord AC, and we also have tangent BP that is tangent to this green semicircle at point P. Therefore, we can implement here rule 10. Okay, we can implement here rule 10. I'll repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is a chord, you can see here that AB is a chord of this circle. And from the common external point P, we have tangent PT that is tangent to this circle here at this point T. Point T is the point of tendency of tangent PT with this circle. So in this drawing, the following equation will be true, that PT squared, that is the square of the tangent PT, is equals to PA times PB. Again, PT squared equals to PA times PB. We can actually implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common external point B, from this common external point B, we have tangent BP that is tangent to this green semicircle at point P. In addition, we have also chord AC that starts from point B. This is the common external point B. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, we get that BP squared equals to BC times BA. Again, BP squared equals to BC times BA. So write it down. According to rule 10, BP squared, that is the square of tangent BP, equals to BC times BA. This equation is the implementation of rule 10 in our drawing. It is given us the question that line segment BC equals to 1 unit in its length, and line segment AB, that's actually the diameter of the white semicircle, line segment AB in total equals to 5 plus 1, that is 6. Again, AB equals to 5 plus 1, that is 6. So here AB equals to 6 units in its length. So BP squared equals to BC times BA. BP is the missing tangent, so we leave it as it is. BP squared equals to BC. BC is 1, therefore we substitute BC by 1 times BA. Just write down for now that BA equals to 6. So in total, BP squared equals to 1 times 6, that is 6. We take the root out of the equation. And finally we get that the missing tangent BP is equals to the square root of 6 units in its length. So this is the missing tangent BP is equals to the square root of 6 units in its length. Okay. So in the next step I copy the right triangle APB in a new page and we implement on this right triangle APB the Pythagoras theorem. AP is the missing side, PB equals to the square root of 6 units in its length, and the hypotenuse AB equals to 6 units in its length. So here, this is the right triangle APB that goes from the original domain. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is AB, therefore the square of the hypotenuse is AB square. And AB square equals to AP square plus PB square. AB equals to 6, therefore AB square is 6 squared, that is 36, and it is equals to AP square. AP is the missing side, so we leave it as it is, AP square plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in conclusion, we can find out that according to the Pythagoras theorem, 36 equals to AP square plus 6. We subtract 6 from this equation, and we get that AP square equals to 36 minus 6, that is 30. AP square equals to 30, we take a root out of this equation, and finally we get that the missing side AP equals to the square root of 30 units in its length. AP equals to the square root of 30 units in its length. This is nice element AP. AP is the diameter of this semicircle, and this equals to the square root of 30 units in its length. If the diameter AP equals to 6, it means that the radius must be equal to half of it. The radius is AP over 2. So the radius is R. So R, the radius of this green semicircle, equals to AP, the diameter AP over 2. AP is square root of 30, therefore the radius R equals to the square root of 30 over 2. Again, the radius of this green semicircle, R equals to the square root of 30 over 2. Again, our mission is to find out the area of this green semicircle, and the area of this green semicircle equals to pi r square over 2. Pi r square over 2. So it is pi, r is square root of 30 over 2, therefore r square is square root of 30 over 2 square divided by 2. We'll open the brackets here, we'll get that the area of the green semicircle in total equals to pi, square root of 30 square is 30, over 2 square is 4, divided by 2. So the area of the green semicircle equals to pi, and 30 over 4 over 2 equals to 30 over 4 times 2. And here we have 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75, so in total this expression equals to 3.75 pi In terms of numbers, it is equal to 11.78 square units. Repeat again. We actually found out that according to the second method, the area of this semicircle equals to either 3.75 pi square units, so in terms of numbers, it is equal to 11.78 square units. Okay, so in the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the area of this green semicircle using two different methods. So in the domain, we have two semicircles. We have this white semicircle and this green semicircle. In addition, we know that this is 97AC, this is equals to 5 units in its length. This is 97CB, this is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first step, we joined points P and B together by a straight line, and then I copied the white semicircle in a new page and we implemented all 7 in the white semicircle. So this is the white semicircle that I call from the original domain. AB is of course the diameter of this semicircle, and by joining points P and B together by a straight line, we created peripheral angle APB. This peripheral angle APB is subtended on AB, that is the diameter of this semicircle, and therefore according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore this peripheral angle APB must be equal to 90 degrees in its size. This angle is a right angle. Okay. In the next step, if we joined points P and C together by a straight line, and then I copied the green semicircle and represent rule 7 on the green semicircle. This is the green semicircle that I copied from the original domain. By joining points P and C together by a straight line, we created peripheral angle ACP. AP is of course the diameter of this green semicircle, and we have peripheral angle ACP that is subtended on AP, that is the diameter of the semicircle, and according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore peripheral angle ACP equals to 90 degrees. It is a right angle. From the original drawing, it is very easy to see that this is angle A, that is a common angle. It belongs both to the green triangle APC, and this angle A also belongs to triangle APB. Therefore, angle A, it is a common angle that belongs to both triangles. So we define this common angle A is alpha. So here, this is the common angle A that we define as alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing third angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle APC, this is angle A, that is a common angle, it belongs to both triangles. Therefore, angle A equals to alpha according to our definition. So in the green triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this further missing angle must be equal to 90 degrees minus alpha. In the next step, I copy those two right triangles in a new page. Copy the green right triangle and this white right triangle in a new page, and we put that the two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that I copied from the original drawing. So in the next step, we put that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. This is a common angle that belongs to both triangles, so I can write out that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the angles in this green triangle APC are correspondingly equal to all the angles of this white triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, actually proved that the white triangle APB is similar to the green triangle APC according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in this right triangle APB or side AP in this green triangle equals to side AP in this right triangle over side AC in this green triangle. Repeat again. We derive that AB over AP equals to AP over AC. AB is 5 plus 1, that is 6, and AC is 5. Again, AB is 6 and AC is 5. So in total, this equation is equals to 6 over AP, that is equals to AP over 5. Because I multiply this equation, we finally found out that 5 times 6, that is 30, equals to AP times AP, that is AP squared. So 30 equals to AP squared. We took out of the equation and finally found out that AP equals to the square root of 30 units in its length. So this is 9/7 AP, that is equals to square root of 30 units in its length. We already found out that AP is the diameter of this green semicircle. If AP is the diameter, it means that AP over 2 is the radius of this green semicircle. So we define the radius of this green semicircle as R. So R equals to the diameter AP over 2. AP is square root of 30, therefore R is square root of 30 over 2. In conclusion, we actually found out that the radius of this green semicircle R equals to the square root of 30 over 2. And our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r squared over 2. Again, the area of the green semicircle, that is the area that we are looking for in this question, equals to pi r squared over 2. So it is pi and r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. We open the brackets here, we found out actually that the area of the green semicircle equals to pi, and the square root of 30 squared is 30, over 2 squared is 4 divided by 2. So the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, this expression equals to 30 pi over 4 times 2. 30 over 2 is 15. So in total, this expression equals to 15 pi over 4. 15 over 4 is 3.75. Therefore, in total, this expression equals to 3.75 pi. Or in terms of numbers, it is 11.78 square units. In conclusion, we should found out that the area of this green semicircle equals to either 3.75 pi square units, so in terms of numbers, the area of this green semicircle equals to 11.78 square units. So we finished with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. the second method, we join points P and B together by straight line. And then I copied the white semicircle in a new page and we implemented rule 7 on the white semicircle. This is the white semicircle that I copied from the original drawing. By joining points P and B together by straight line, we created triangle APB. We already found out that AB is the diameter of this semicircle, and we have triangle APB that is subtended on AB that is the diameter of this semicircle, and according to rule 7, any triangle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this triangle APB equals to 90 degrees in its size. So here we have line 7BP is perpendicular to PA. Again, line 7BP is perpendicular to PA because this angle equals to 90 degrees. But what is AP? AP is the diameter of the green semicircle. If AP is the diameter, it means that AP over 2 is the radius. So we defined the center of this green semicircle as point O. So point O is the center of this green semicircle. If point O is the center of the green semicircle, it means that PO is the radius of the green semicircle. Repeat again. AP is the diameter of this green semicircle. We define the center of this green semicircle, this point is point O. If point O is the center of the green semicircle, it means that PO is the radius of this green semicircle, so we define the radius of this green semicircle as R. So in the drawing we have line segment BP is perpendicular to PO, that is the radius of this green semicircle. Again, line segment BP is perpendicular to the radius of this green semicircle, PO, that is equals to R. And whenever you have a line segment that is perpendicular to the radius, you can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius OM that is equal to R. We have a circle, and we have line segment AB that is perpendicular to the radius MO. Again, line segment AB is perpendicular to MO, and therefore, according to this rule, rule 1, whenever you have a line segment that is perpendicular to the radius, then this line segment must be defined as a tangent. So we have here tangent AB is perpendicular to the radius MO. So whenever we have a line segment that is perpendicular to the radius, then the line segment must be defined as a tangent. So we have here tangent AB. This is perpendicular to the radius MO. So we can implement rule 1 in our drawing. In our drawing, this is line segment BP that is perpendicular to the radius PO. And according to rule 1, whenever you have a line segment that is perpendicular to the radius, then this line segment must be defined as a tangent to this semicircle, green semicircle. Therefore, we have here BP is tangent to this green semicircle at point P, according to rule 1. Again, BP, line segment BP is tangent to this green semicircle at point P. And in addition, from the same convex point, point B, we have this is the straight line BA that cuts this semicircle to points, point C and points A. And therefore, by drawing the straight line from point B to A, we created here chord CA. We have here chord from the convex point B, we have chord CA, and from the same convex point B, we have tangent BP that is tangent to this green semicircle at point P. Therefore, all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, BP square equals to BC times BA. Again, BP square equals to BC times BA. Okay. BP is the missing side, so we leave it as it is. BC equals to 1, BA equals to 6, and therefore BP squared equals to 1 times 6, that is 6. BP squared equals to 6, we took out of the equation and finally found out that the missing side tangent BP equals to the square root of 6 units in its length. Okay, so in the next step, I copied the right triangle APB in a new page and implemented the Pythagoras theorem on this right triangle APB. We already found out that PB equals to the square root of 6 units in its length. The hypotenuse AB is equals to 6. The only missing side is side AP. We find out the value of the missing side AP by implementing the Pythagoras theorem on this right triangle APB. So actually, this is the right triangle APB that according to the invariant domain, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse in this right triangle is AB, therefore the square of the hypotenuse is AB square, and AB square equals to AP square plus PB square. Again, AB square equals to AP square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36, and it is equals to AP square plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So if we found out that 36 equals to AP square plus 6, we subtract 6 from this equation, and finally found out that AP square equals to 36 minus 6 is 30. AP square equals to 30, we took out all of the equation, and finally found out that the missing side AP equals to the square root of 30 units in its length. This is the missing side AP. This is equals to the square root of 30 units in its length. But AP is the diameter of this green semicircle. If AP is the diameter, it means that the radius of this green semicircle must be equal to half of it. It must be equal to AP over 2. Again, the radius of the green semicircle equals to the diameter AP over 2. The diameter AP is square root of 30, and the diameter over 2, that is the radius of the green semicircle, is square root of 30 over 2. So the radius of this green semicircle R equals to the square root of 30 over 2. And our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r square over 2. And again, the area of the green semicircle equals to pi r square over 2. So it is pi, r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. We open the brackets here and found out that actually the area of the green semicircle in total equals to pi times square root of 30 square is 30, over 2 square is 4 over 2. So the area of the green semicircle in total equals to pi times 30 over 4 over 2 is 30 times 30 over 4 times 2. So the area of the green semicircle in total equals to 30 pi over 4 times 2. 30 over 2 is 15. Therefore, this expression in total equals to 15 pi over 4. 15 over 4 is 3.75. So in total, this expression equals to 3.75 pi. In terms of numbers, it is 11.78 square units. So we found out that according to the second method, the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. So in both methods, we arrived to the same result. Okay, thank you very much.